Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to have you biology students here with us because today we are going to unpack some of the most profound biological mysteries and extremes found anywhere in nature. We're going to look at physiological adaptations that, quite frankly, seem to completely defy the very rules of biology we learn in our textbooks. We are talking about the sheer miraculous physiology of hibernating animals.
Okay, let's dive right into our roadmap for today. We're going to cover 1. The extremes of hibernation. 2. Surviving ischemia and reperfusion. 3. Hacking the thirst signal. 4. Muscle retention and urea recycling. 5. Medical applications. And finally, 6. The philosophical conclusion.
So first up, Section 1, the absolute extremes of hibernation. To really appreciate how wild this gets, we've got to set a baseline. Picture a common ground squirrel in its normal, active state during the summer. It's darting around, foraging, eating, and breathing rapidly. Right now, its heart is beating at an astonishing rate of 300 beats per minute. This is a highly active, high-metabolism mammal, firing on literally all cylinders to survive and prepare for the winter.
But then, winter arrives. The squirrel retreats into its den, and that baseline, it completely shatters. During hibernation, that rapid heartbeat plummets from 300 down to just 3 beats per minute. Think about that for a second. The heart practically stops. It enters this state of extreme bradycardia that honestly would be immediately fatal to a human.
And accompanying that slowed heart is a dramatic metabolic depression. The oxygen consumption of the hibernating squirrel drops to a mere 2% of its normal active state. The animal's cellular respiration slows to an absolute crawl. It is barely taking in any oxygen at all, yet remarkably, its cells remain perfectly viable.
And the extremes do not stop at the heart and lungs. The squirrel's body temperature drops from a warm-blooded mammalian norm all the way down to 5 degrees Celsius, just above freezing. It sits in this frigid, suspended animation for months without a single drop of water or a single calorie of food. Yet when spring arrives, in just a matter of a couple of hours, the squirrel perfectly reboots its system back to 37 degrees Celsius and just scurries right out of its den.
All right, moving on to Section 2, surviving ischemia and reperfusion.
Let's put on our clinical hats for a second and use a bit of the Socratic method. What happens to a human being when blood flow severely drops and brain or heart tissue is deprived of oxygen? Well, we know the answer. Ischemia leads to a stroke or a myocardial infarction, a heart attack. Tissues die incredibly fast when starved of oxygen. But the squirrel's blood flow drops to almost nothing and it suffers absolutely zero tissue death.
But the mystery goes even deeper than that. Take this observation from Professor Matthew Andrews over at the University of Minnesota. He points out that the greatest tissue damage in a human stroke or heart attack patient actually occurs not when the blood flow decreases, but when the flow returns to normal. It's this concept known as reperfusion injury. When oxygen-rich blood suddenly rushes back into oxygen-starved tissues, it creates massive oxidative stress and inflammation, basically destroying the cells. So it's a dual danger, right? The blood leaving and the blood rushing back.
Yet somehow, the squirrel survives both phases completely untouched. Research from the Stanford University Medical School actually shows that the squirrel's waking process, when its heart rate spikes wildly to warm the body up, closely mimics the physiological events of a human heart attack. The blood rushes back forcefully. But the animal emerges completely unscathed, with zero reperfusion injury. Its cells literally have a built-in defense mechanism against oxidative stress that we are still trying to figure out.
Which brings us to Section 3, hacking the thirst signal. We've already established the squirrel goes months without water, which brings up a huge mystery regarding osmoregulation. I mean, surely it must be agonizingly thirsty, right? Well, actually no. Research led by Dr. Elena Gracheva at Yale University found that these hibernating squirrels do not even feel the sensation of thirst, despite enduring months of absolute dehydration. Their biological thirst mechanism is entirely suppressed.
So how exactly do they do it? Through this incredible process of serum concentration manipulation. In a normal mammal, when water drops, electrolytes like sodium and compounds like glucose become highly concentrated in the blood. This spikes the serum osmolality, which then triggers the brain's thirst receptors. But the squirrel actively sequesters these electrolytes and glucose away from the bloodstream, storing them elsewhere in the body. This keeps the blood serum concentration artificially low, so the brain never even receives the signal to feel thirsty. In fact, Dr. Gracheva's researchers actually had to artificially inject the squirrels to raise their serum concentration just to force them to feel thirst.
Okay, Section 4, muscle retention and urea recycling.
Let's zoom out a bit from the microscopic and look at bears to illustrate the sheer efficiency of hibernation. If a human is bedridden for just 3 months, even while receiving a perfectly balanced diet, they're going to suffer a massive 54% loss in muscle mass due to atrophy. Now look at the bear. The bear's in its den for 4 months, not moving, fasting completely, and burning 4,000 calories of fat a day just to stay alive. Yet it only loses about 29% of its muscle strength.
As biology students, you know this shouldn't be possible. Without dietary protein, those muscles should just waste away. But the bear relies on a true metabolic miracle, urea recycling. Step 1. The bear doesn't urinate for months. Step 2. Urea, which is normally a highly toxic waste product that mammals have to excrete, is instead chemically broken down inside the bear's body. Step 3. This breakdown releases raw nitrogen. And step 4, the bear's body captures that nitrogen and synthesizes it into brand new amino acids, building fresh proteins to maintain its muscle mass. It is the perfect, closed-loop recycling system, turning toxic waste into muscle preservation. Crazy, right?
Now, Section 5, medical applications.
Why does all this matter to us? Well, look around the globe. The medical world spends billions upon billions of dollars utilizing the most advanced laboratories in existence, all dedicated to 3 major goals: preventing strokes, preventing heart attacks, and stopping muscle atrophy in bedridden or aging patients. We are desperately trying to artificially engineer solutions to these immense health crises.
Yet a simple squirrel and a bear pull this off every single winter, spontaneously, automatically, and with absolutely zero external medication. They do effortlessly what our greatest medical minds are struggling to replicate. Scientists are dedicating their entire careers to studying these animals, trying to unlock the unsolved questions of this biological system so we can apply these exact mechanisms to human medicine. The sheer biological efficiency is simply staggering.
And finally, Section 6, the philosophical conclusion.
Having looked at the empirical data, the source material actually pivots here to draw some teleological conclusions. The text presents a perspective drawn from Islamic theology, specifically quoting the 42nd verse of the Zumar Surah. The text reads, "Allah takes souls at the time of their death and those that do not die during their sleep." The author of the source material uses this verse to draw a really interesting philosophical parallel. They compare the extreme physiological state of hibernation, where the heart slows to a crawl and breath practically pauses, to the concept of sleep being a state akin to near death. The animal enters this void, suspended right between life and death.
But of course, as spring arrives, the animal always returns. The hibernation reverses, the heart speeds up, and life resumes perfectly. And so, reflecting on the sheer complexity of the ischemia survival, the thirst hacking, and the urea recycling, the source material leaves us with a final provocative thought to ponder. Considering the sheer perfection and automatic nature of this biological programming, the text asks, and the system that enables this return, who wrote it into them?